Hello, this is Math Jazz from Almost Cool, and for today's live stream, we are going to talk about matrices. So, um, we were talking about matrices on Friday last week, and we will continue where we left off, which I believe was row reduction. So, without any further ado, let us talk about row reduction. So, first thing that we need to talk about for this is reduced row echelon form. So, our reduced row echelon form, whenever we have a matrix of this form, where we have ones on the main diagonal, remember the main diagonal starts on the upper left corner of the matrix and goes down one and over one, like so. Down one, over one, down one, over one, until it hits the side or bottom of the matrix. When we have a matrix that is all ones on the diagonal and zeros off of it, we are in reduced row echelon form. We can have anything we want outside of that. So when we have a matrix that's in this form, this is equivalent to having a solution to a linear system. So if we had some sort of set of equations in x, y, and z, then this tells us that one x is equal to 17, 1y is equal to 8, and 1z is equal to 5. So let's practice converting a system from our linear system form into a matrix. Here, we'll get a system. How about x minus y plus z equals 3, and we'll do 2x minus 2y plus z equals 4, and we'll have x plus y plus z equals 9. So here's our system. We're going to convert this into a matrix, and then we're going to row reduce it until we get into row echelon form. So from this matrix, from this system, we get this matrix. We have 1x, 2x, and 1x is our first column. Then we have negative 1y, negative 2y, and 1y as our second column. We have 1s down the third column, and we have a 3, a 4, and a 9 representing our constants on the opposite side of the equal signs. We need to have all the variables on one side and all of the constants on the other side for our matrix to work properly. So from here, to get this in row echelon form, we're allowed to add rows to other rows, and we're allowed to multiply rows by constants. So what I'm going to do is I'm going to take this first row, and I'm going to subtract 2 copies of it from the second row and 1 copy from the third. So I'm going to have R2 minus 2R1 goes to R2, and R3 minus R1 goes to R3. You don't have to write this, but I like to because it shows what I'm doing so I don't mess up. Anyway, the first column I'm not changing, so I'm just going to the first row I'm not changing, so I'm just going to copy the row over, like so. So 1, negative 1, 1, 3. The next row, I have 2 minus 2 times 1 is 0. Negative 2 minus 2 times negative 1 is the same as negative 2 plus 2, which is 0. I have 1 minus 2 times 1, negative 1. And 4 minus 2 times 3 is negative 2. 1 minus 1 is 0. 1 minus negative 1 is 2. 1 minus 1 is 0. 9 minus 3 is 6. Okay. From here, this is our new matrix. I'm going to take it, and I'm going to divide the bottom row by 2. So I'm just going to write that as 1/2 R3. And that half of R3 I'm going to add to the first row to knock out this term here. So from here, I get my new matrix, which will go 1, 0, 0, 0, negative 1, negative 2, 1, 0, 3, and negative 1 plus 1 is 0. 1 plus 0 is 1. 3 plus 3 is 6. And then my last move, I'm going to take this row here and add it to this row here. So the second row plus the first row to kill off this 1. I get 1, 0, 0, 0, 0, 1. Negative 1 plus 1 is 0. Negative 2 plus 6 is 4. I didn't change the third row in this operation. I have this, so I'm going to now swap the third and second row. This is my notation for that. I'm also going to multiply the second row by negative 1. So I get as my final matrix 1, 0, 0, 4, 0, 1, 0, 3, and 0, 0, 1, 2 as my final matrix. And I claim that that is a solution to our original matrix. So, to check, to our original linear system. So to check, what I claim is that x equals 4, y equals 3, and z equals 2. If we go up to our original system here, we have 4 minus 3 plus 2 is 3. 8 minus 6 plus 2 is 4. 4 plus 3 plus 2 is 9. So, in fact, our solution x, y, z equals 4, 3, 2 works. Great. Well, so we now know how to reduce a matrix, but we don't know how to add them, and we don't know how to multiply them. So we're going to learn how to do that right now. So if two matrices have the same dimensions, then we can add them. And we add them entry by entry. And what I mean by that is so let's say that we have this is our matrix here. This one is in reduced row echelon form. This is also called the identity matrix for reasons that we'll get to later. But if I have this 3 by 3 matrix and I'm adding this other 3 by 3 matrix, I go, here's the top right entry, 1. Here's the top right entry, 1. When I add them, I get 2. And then 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. 1 plus 5 is 6. 0 plus 6 is 6. 0 plus 7 is 7. 0 plus 8 is 8. And 1 plus 9 is 10. So this is what I get when I add these matrices. You add them coordinate by coordinate. And you think, oh, well, that's exactly what I expected. Or maybe it wasn't, but it probably was. Well, then you're thinking multiplication would be the same. And it is not. Multiplication of matrices happens in a strange pattern which, well, it seems strange at first, but there are good reasons for having matrix multiplication this way that we might get into in a future video. But let's say that we have a matrix. Let's have it be a small matrix, a 2 by 2 matrix. So not the smallest we could make, but pretty close to it. This is how we're going to multiply these matrices. So you take the first row, multiply by the first column, 1 times 0 and 2 times 6, and then you add those numbers together, and that becomes the top left coordinate of your new matrix. So 1 times 0 plus 2 times 6 is going to be this entry here, where we go first entry, first row, first entry of the first row times the first entry of the first column plus the second entry of the first row times the second entry in the first column, and so on. If there were a third entry in this row and a third entry in this column, it'd go third by third. Okay? And since it is the first column and the first row that we multiplied together, that goes in the spot of the first column and first row, the top left. Next, we're going to take this row and the same column and go 3 times 0 plus 4 times 6. So that's the first entry of the second column times first entry of the second row times the first entry in the first column plus the second entry in the second row times the second entry in the first column. And because it is the second row and the first column, the entry goes in the second row and first column of our new matrix. So now we do the same thing to the second row here. So we have 1 times 5 plus 2 times 0. Since it's in the top row of the first matrix and the right column of the second matrix, it goes in the top right position in the matrix. So that's 1 times 5 plus 2 times 0. And the next one, we take the bottom row and the right column, and we multiply them together, we get 3 times 5 plus 4 times 0. And now that we have this matrix here, well, we're going to simplify all of the addition and multiplication there. So we get 1 times 0 plus 2 times 6 is 12. 1 times 5 plus 2 times 0 is 5. 3 times 0 plus 4 times 6 is 24. And 3 times 5 plus 4 times 0 is 15. So this is our matrix product. So we might want to see this again. Maybe this time with a slightly bigger matrix. So let's try. Here we'll have 1, 2, 3, 4, 5, 6 as our first matrix, and we'll have 0, 1, 2, 3, 4, 0. I want to put a few zeros in there because it simplifies the product, and I think it'll still illustrate the point. So one thing that's important in multiplying matrices is that you need to have the same number of columns on the first matrix as you have rows on the second matrix. So we need to multiply 1 by this 0, 2 by this 2, and 3 by this 4. If you run out of rows or columns, then your dimensions don't match and the matrix doesn't have the product that you asked it to have. So 1 times 0 is 0, plus 2 times 2 is 4, plus 3 times 4 is 12, so 4 plus 12 is 16. That goes here. 4 times 0 is 0, 2 times 5 is 10, 6 times 4 is 24, 10 plus 24 is 34. Now we move to the next column. 1 times 1 is 1, 2 times 3 is 6, 3 times 0 is 0, 1 plus 6 is 7. 4 times 1 is 4, 5 times 3 is 15, 6 times 0 is 0, so 4 plus 15 is 19. So we multiplied a 2 by 3 matrix by a 3 by 2 matrix and got a 2 by 2 matrix as the result. In general, the number of rows on the first matrix is the number of rows in the product, and the number of columns in the second matrix is the number of columns in the product. Okay, so now let's talk about another thing that that matrices have. We talked about reducing matrices. We talked about adding matrices, and we talked about multiplying matrices. Now we're going to talk about determinants of matrices. So, determinant of a matrix is kind of like, we want to think of it as kind of like the absolute value of a matrix, although absolute value is something that numbers have, not matrices. The determinant is kind of like the closest thing that we have to the absolute value of a matrix. So the determinant of some matrix, I'm going to write a matrix like 1, 2, 3, 4. Now, we're going to give formulas for 2 by 2 matrix determinants and 3 by 3 matrix determinants. But we're probably not going to do any determinants of higher dimension than that. And I mean, there might be a video in the future where we show that, but we're going to stick with 2 by 2 and 3 by 3 matrices for now. So we have this determinant of a matrix, which looks like this. We're going to take the diagonal entries, 1 and 4, and we're going to multiply them together. And we're going to take the anti-diagonal entries, which are 2 and 3, and we're going to multiply those together, and we're going to take the difference of the two of them. So 1 times 4 minus 3 times 2, that will be negative 2. And I said it's kind of like an absolute value. The determinant can be negative. Absolute values are only positive. But the determinant is kind of like an absolute value of the matrix. Now, what happens if we switch the two rows of this matrix? Let's say that we take the determinant now of 3, 4, 1, 2. We switch the two rows. Well, now we have 3 times 2 minus 4 times 1, and that equals positive 2. Turns out whenever you switch rows on a matrix, the determinant will switch signs. And it works just the same for columns. So the determinant of 2, 4, 1, 3 is going to equal 2 times 3 plus 4 times 1, which is going to equal, sorry, not plus, minus 4 times 1. The anti-diagonal gets a minus sign on it. That's going to be 2 as well. So switching the rows or the columns will change the sign of your determinant. And this isn't a proof, but we could put a proof in another video. Now, how do we take a 3 by 3 determinant? Well, I'm going to add some zeros in this just to make the determinant less cumbersome to compute. I might add a few negative numbers too. Great. So, with a 3 by 3 matrix, we're going to compute the diagonal and the triples that are kind of parallel to the diagonals. We're going to take those products together. So this will be 1 times 1 times 0. That's this diagonal, the main diagonal, plus 2 times negative 2 times 0, which is this diagonal, 2, negative 2, and hook around to grab the 0, plus negative 1 times 2 and hook around to grab that 0. Okay, so those are our positive 3 products. Here they are. And now we're going to grab our negative 3 products. So our negative products are going to go perpendicular to our positive products. One's going to be the anti-diagonal. One's going to be this 2, this negative 1, and hook around to catch the 0. The other is going to be this negative 2, this positive 2, and hook around to catch that 1. Those are what we're going to call our negative diagonals. So they are 0 times 1 times 0, and all of these will be negative. So plus negative 2 times 2 times 1 plus 2 times negative 1 times 0. These are our 3 negative terms. So notice that in this case our positive terms or positive diagonals all came out to be 0 because each of them has a 0 in them. 2 of our negative diagonals came out to be 0 because of the zeros in them. We're left with a negative 2 times 2 times 1. So that's going to be a 4. And let's see this again with another matrix. We're going to feel very good about taking determinants by the end of the video. So let's see. Have 1, 1, 1, 1. Let's put a negative 1, 1, and negative 1, 1, 1. Okay, so we have this matrix that we're going to take the determinant of. So we do 1 times negative 1 times 1. That's our first positive diagonal. The ones that slope down to the right are going to be our positive diagonals. And then we have 1 times 1 times negative 1. That's this diagonal. It's these two and hooks over and hits this corner. Plus 1 times 1 times 1. That's going to be these two and hook around to hit that corner. Now we need to get our 3 anti-diagonals, or negative diagonals I've been calling them. So we have minus -1 times -1 times 1 plus 1, 1, and 1 plus 1, 1, and 1. Great. So, simplifying this, we have -1 is our first product, -1 is our second product, and 1 is our third product, minus 1 plus 1 plus 1. So that gives us, this isn't a 3, this is a 1. 1 times 1 times 1 is 1. That gives us -1 minus 3, which equals -4. That is our determinant for this matrix. And you might be wondering, what is a geometric interpretation of the determinant? Well, I didn't give you one for multiplication, but I will give you one for the determinant. So what we want to imagine for what the determinant means is we're going to take our XYZ coordinate system. Here's our X, our Y, and our Z. And we're going to think of each of these here as being points in space. So we have the point 1, 1, 1, and the point, this is 1 in the X direction, 1 in the Y direction, and 1 in the Z direction. Guess we'll put it here. And then we have 1 in the X, -1 in the Y, and 1 in the Z here. And then we have -1 in the X, and then 1 in the Y, and 1 in the Z. I guess all of these are above the plane. And then we're going to take our origin here, connect each of these 3 points to the origin, and then we're going to make those into the, we have a point here, a point here, a point here. We're going to take this line and make a parallel one here, and we're going to take this line and make a parallel one here, and then close these off, make a parallel one here. And what ends up happening is we have, well, it's going to be, it's called a parallelepiped, and I'm going to try and draw one of those so that you get an idea of what shape we're looking at. So it looks kind of like a box that maybe someone sat on it so that the sides aren't rectangular anymore. They're not, nice right angles. But each of the sides of this thing is a rectangle. It's just they don't meet up into nice 90-degree angles anymore, each of these rectangles. So we have kind of like an eraser. If you remember the little pink erasers that you'd use in elementary school, that's the kind of shape that we're talking about. So these here become points, and they become, here's the origin. You get 1 point for each, 1 point here, 1 point there, 1 point there. The ones that connect to the origin become the 3 corners on a parallelepiped that connect to the origin, and then you just take each side, like from the origin to this point, slide it so that you can find a 5th point here, and then slide this point up to here, so you find a 6th point there, 7th point there, 8th point there, and now you have your whole parallelepiped, and the determinant, the absolute value of the determinant is the volume of that parallelepiped. And the sign is positive or negative depending on which direction you go, going from the origin to each of these points, whether you're going clockwise or counterclockwise when you're traveling from the origin to this point, and then the origin to that point, and the origin to that point. If it goes looking down 1, 2, 3, it's going to be one sign, and if you flip it so it goes 1, 2, 3. So going around this way will be positive, going around that way will be negative, or vice versa, depending on how your points are in relation to each other. But switching the sign is reflected by switching which direction your points, or which order your points are labeled here. Going around one way will be positive, going around another way will be negative. So that is a geometric interpretation of the determinant. It has to do with volumes of lopsided boxes, where the points that determine the ends of the boxes are your rows in your determinant, or the rows in your matrix. Anyway, hope you enjoyed watching, and we will see you tomorrow, where we'll probably work on linear regressions, and maybe pick up some extra matrix stuff. So, see you tomorrow. Hope you're having fun learning math, and bye.